So this is the second video where I'm trying to explain why Lagrange multipliers work. So I've gone through a bunch of stuff. I talked about parallel vectors. I talked about contours and them being perpendicular to level curves being perpendicular to the gradient of a function. And then we talked about how that is also true for the constraint function if I look at the constraint function as its own multivariable function, g of xy equals a constant. So now I'm going to pull in an example that I hope will help you see how all that fits together with Lagrange. So I want to maximize and minimize this function, f of xy equals x squared plus 2y squared, subject to the constraint, the unit circle. So you see right here, this is that function. It's a paraboloid. It opens up. One thing I'm going to point out is that I don't have this axis oriented in the way that it would normally be oriented. Normally, the x-axis, the positive x, would come out this way. This red axis is the positive x-axis, and this green axis is the positive y-axis. I have it spun like that so that the orientation of this will fit when I put the xy coordinate grid out looking at contour plots. It is still a right-hand system. So what I've attempted to do here is to draw the constraint on the xy plane. This part right here should be behind that parabola. And then it swings out in front. This is over here, over there, and then right there it swings behind that, right? So I want you to see that that is the constraint, right? Now what I want you to do is imagine lifting that constraint circle up and letting it like leave a shadow the whole time until all of the different parts of it hit the parabola. And I actually have an image of that, so let me bring that in. There it is. It's much better than I could have drawn if I had tried to sketch that in. But lift it up and it would hit in all these different spots. And then I've got this surface that kind of goes around like that. And I'm going to show you in the grapher that I used in a moment. But see that right there, that looks like the high point. And then it's going to dip back down in the back, right? Just like it dips down here because of the symmetry of this thing. And that right there looks like the low point. So the spots where this red cylinder hits the blue paraboloid are the spots that I want to inspect. That is where this multivariable function is subject to that constraint. Hopefully, I think that right there would be the maximum. The height, the z value there. And this over here is probably going to be the minimum because I think that it's the same on either side. So here's that image using the GeoGebra 3D calculator. And watch, I can throw this guy in here. And what I can do is spin it. And you can see that high point, the intersection right there, if I could like look straight down like that, almost, you see that's a circle, right? And it intersects the parabola on that unit circle, but then leaves this in 3 dimensions, this kind of wavy looking line if I were to trace around the intersection of these two spots. So what we're going to do next is talk about what has to be true with relation to the constraint function, the unit circle, and the level curves of this blue surface in order to get to that high point right there. I think you should see that is like that. This z value right here is what we're looking for. And that y value, or that z value right there is what we're looking for the min. So if I can find a way to get to those two spots, then I will have completed this Lagrange problem. Okay, what I have here is the level curves for that function plotted as a contour plot. I started at 0, which would have been here. There's no actual curve. It's just a point. And then I bumped by 0.2s. Notice these guys get closer as we get further out, which is indicative of this thing getting steeper, right? The tighter the level curves are together, the steeper that function is at that spot. So I want you to imagine drawing the unit circle over top of this thing. And let me show you a couple spots here for the unit circle. We got a spot there, we got a spot there, we got a spot there, and we got a spot there. So what would it look like if we were to draw the unit circle there? And remember, the reason I'm doing the unit circle is because that is my constraint, right? That's the constraint we're working with, right? So imagine that. I'm gonna throw it up in a moment. So there it is, right there. I've got, and actually, it's kind of like one of those optical illusion things. It doesn't look like the red one's a circle, at least to my eyes, it doesn't. But that's because I guess it's embedded in these ellipses. But look, it does go through 1, -1, 1, -1, and it's a circle. It's not an ellipse, right? So anyway, that is my that's my constraint. So I want to find the spot on this function, on this contour plot, such that this is the highest, such that it is the highest and the lowest values of the contour. I would argue that it has to be there, 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 or there, or there. Those are the spots we care about. Why is that? It's because these are parallel. And let me pull up the other function so you can see why that has to be true. Okay, so I have a zoomed in version of this right here. And I think that this will finally connect if it hasn't already. Okay, so think about what these level curves mean. It is where the blue paraboloid is constant, where its height on the z is constant. So for example, I could a little purple line there, right? And I tried to put the dots in the back so you can tell what's in the front and the back. But that would be a level curve, right? So now what I'm going to do is draw a level curve down lower. Here, this level curve is clearly, it hits that intersection between the two surfaces here. It's not at the high point, and it's clearly not at the low point. I would argue that that has to be like one of, not that one, like one of these right here. Why is that? Well, look, this curve that I drew here intersects right there. And then it's going to intersect in three other spots. One over here, one back behind there, and then maybe one over here. It's going to intersect in those spots, right? So those four intersections are this spot, and this spot, and this spot, and this spot. So what's going to happen is in the space in which we're on that wavy thing, right? The intersection of those two. If the level curves, the purple, and the constraint intersection, if they intersect each other and cross, then we're at like this one or this one. We're at those crosses right there, right? And what I would argue is if we're trying to find the minimum or the maximum, well, I could take this level curve and I could move it up, right? Which level curve is going to hit that high point right there? It's gotta be this thick purple one right here. Look at that. What happens? It just skims it. They are tangent, right? But imagine taking this surface and spinning it. So that surface, I can't draw the level curve on GeoGebra, but imagine I were to draw that level curve and I were to spin it and the level curve were to move with it. And I go until up, I'm looking straight down the z-axis. I'll stop right there.